Welcome to lecture 4.2, where we're focusing on resonance for positively charged molecules. Now, first things first, I want to kind of discuss what I think of when I think of a positively charged molecule, and that is that it's a molecule with electron deficiency. Now, since this is a course targeted towards Canadian students, this would be a good time to bring up housing. And the way I like to think about this is that the atoms are potential houses for your molecules, for your electrons. And we have four houses here. Now, in a perfectly balanced molecule where there is no charge, you would see electrons in every single atom. However, with electron deficiency, that means that some atoms are missing the amount of electrons that they need, which is the same as saying we have an empty house. Now, when it comes to resonance forms, that's good. That'll really help us understand rule number 2 of resonance forms, which is to give those electrons a good home. If we're going to be moving electrons around, it makes sense that we're going to be moving those electrons into that empty house. So that's one metaphor I like to think about. Another thing you're going to see when we're dealing with positive charges in resonance is the use of bond-to-bond arrows. And you'll see what I mean in a moment. So the first kind of resonance I want to cover is something called allylic resonance. Now, allylic might be a new word, but really what this means is the resonance of an alkene. So allylic means adjacent to an alkene. This right here, in this example molecule, we have a 3-carbon compound. It looks very similar to the example I used in the previous lecture, but now we have a positive charge here. And to be clear, that means that we have only 2 hydrogens here, as if we had a third, it wouldn't be positive. This is a carbocation after all. Now, when you're one away from a double bond, we can call this the allylic position, and that's where that name comes from. It's one away from an alkene. So let's consider the resonance of this molecule, and we'll draw in the hydrogens to make sure we don't fall for the same trap we did last time. So we have our loosely held electrons, highlighted in red, our pi bond, and our positive charge, or our empty house, over here. And what this will allow us to do is to take this double bond, and now we're going to be able to move the electrons between atoms 2 and 3. The resonance form that this gives us, again, using the resonance arrow, is electrons between carbon 2 and 3 in a pi bond. Now, if we look at the hydrogens again, carbon 3 is now satisfied. It has its 4 bonds. Carbon 2, as always, doesn't really care, but carbon 1 still only has its 2 hydrogens, which now means that the positive charge has moved to carbon 1. Now, a common mistake students will make is moving the positive charge with an arrow, and that is always going to be incorrect. And the reason for that is that these curvy arrows indicate the movement of electrons, and that's something we'll touch on later in the course when we get to reaction mechanisms. But a positive charge is a place where electrons are not. So moving a positive charge like this is never going to be correct. You'll notice here that the arrow starts from a bond and takes those 2 electrons and moves them to a different bond. We went pi bond to pi bond, and that's what I mean by bond-to-bond arrows. Resonance can seem overwhelming at first, but when you notice a lot of these trends, you'll see that there isn't actually that many types of resonance. And when you're dealing with a positive charge, this bond-to-bond idea may be very helpful. So what we have now is 2 equally stable resonance forms. They both have a positive charge, a carbocation. This form is on the 3rd carbon, and for the form over here, it's on the 1st carbon. Now, the reason that this is, we brought up earlier the idea of the colors mixing with resonance. If this was an equilibrium arrow, like this, what this would indicate to us is that we have 2 different types of molecules. Now, they're both identical, just flipped over, but in theory, we would have 2 molecules that have a double bond and a positive charge on each. And if that was the case, it wouldn't really make sense why resonance is stabilizing and why we care about it so much. But it's when we consider the mixing of these 2 molecules that we start to see that value. Now, let's draw this. So importantly, these here are equally stable. These 2 different resonance forms. And only when they're equally stable are you able to draw what's called a resonance hybrid. Or at least an accurate resonance hybrid. Now what that's going to look like is we're going to draw all the single bonds that we had. Those are never allowed to move in our resonance hybrid, So we have our bonds between carbons 1, 2, and 3, and we have all of our hydrogens. Now, this is the interesting part. Since these are equally stable, we can make the assumption that each of them contributes 50% to the total, 50% each, to the total resonance hybrid. So let's call this form A and form B. Form A has a positive charge on carbon 3, while form B has that positive charge on carbon 1. If we assume that they both contribute half of their character to the overall hybrid, what that means is that essentially the molecule would have a positive charge on carbon 3, but half the time, or half of a positive charge. And we can actually illustrate this by writing plus 1/2. Meanwhile, the other half charge will be found on carbon 1. And essentially what we've done here is we've split the positive charge over 2 atoms by cutting it in half. The overall charge of the resonance hybrid, of course, is still positive 1. That hasn't changed. Now, the way we're going to deal with the double bond is also similar. In resonance form A, carbons 1 to 2 are double bonded, but that is not the case in carbon B, where they're single bonded. And so what we're going to do is use a partial bond, which we can illustrate by using a dotted line. And this is to say that we're somewhere between a single bond and a double bond, a partial double bond, if you will. That's also true for carbons 2 to 3. And so essentially what we have is this nice happy mixture of electrons throughout the whole molecule, with that positive charge split between atoms 1 and 3. Now, let's answer the big elephant in the room question. With this knowledge, why is resonance good? Why is it stabilizing? And the answer has to do with a metaphor that I like to use, which is, let's imagine a grenade. And what I always like to ask is, what makes a grenade scary? You might say, well, it explodes, and that's absolutely reasonable, right? That's pretty scary. Is it the energy of the grenade? Is it the amount of energy that it possesses? Well, not really. I'll gladly get into a car with a combustion engine and drive it for an hour. The amount of energy that that engine is producing is far greater than any grenade. What makes the grenade scary is that it's a concentrated place where there's concentrated energy, right? It's all that energy in one small container. That's what makes it scary. If you were to take all the explosives out of a grenade, spread it across a football field, and miraculously it all exploded at once, you might not even hear it, right? We would call this, another word for concentrated is localized energy. It's in one space. So we can view this positive charge the same way. We know that a positive charge on a carbon is not a good thing. It's very destabilizing. But with resonance, we're able to take that positive charge and spread it out, right? Similar to taking that grenade and splitting it into smaller pieces. And by doing so, we do something called delocalization, which is a pretty scary word when you hear it the first time, but really isn't so bad. Delocalization is simply spreading out the charge. So resonance is an objective fact of our universe, whereby we're actually going to be stabilizing that positive charge when there's an alkene beside it. Again, the alternative here would be comparing it to a regular carbocation like this, without the alkene. This molecule would be far more stable. Now, considering all this, there's one more, way you might see this in a very similar case, which is a longer molecule. And this has to do with electron pushing. So in a question like this, you may be asked to draw all the resonance form of a molecule, or all the resonance forms of a molecule like this. Now, to do this, there are 2 ways you can go about it. The first thing I would say is, well, we have a positive charge on this terminal carbon. The orange double bond is nearby. Note that we're not going to be able to use these red electrons. They're too far away from the positive charge. We can't make arrows that go across the molecule like this. However, the orange electrons are very close, and so we could say, well, let's move these electrons to that double bond. This would work since we had a positive charge there, and the new positive charge would be generated in the middle. Now at this point, the red electrons would be able to move, since the positive charge is closer to them. And this would reveal our next major resonance form, which looks something like this. Now the positive charge is on the other side of the molecule. Now what's interesting here is we can actually redraw this original molecule. And go directly to this resonance form from it. The way we're going to do that is via electron pushing. So essentially, we can keep putting arrows and moving electrons around as long as we don't break our rules. We can't break any single bonds, and we need to eventually put those electrons in a good home. So here we have our red double bond, and we can move it to this bond. Now, right now, this is a problem if we look at this. And the reason is that if we look at the central atom, we have a hydrogen here. It's full, right? So I can't make, right? In theory, if I just used that arrow, the molecule I would make would look something like this. And that isn't going to work because we have too many things connected to that carbon. So I guess we can't do that. Well, no, we can do that as long as we continue to push. Since this carbon in the middle is connected to the orange double bond, we can then push the orange double bond there. And in one step, if we follow those arrows, we can draw our skeleton again. The red electrons have moved to this bond, and the orange electrons have moved over here. The positive charge moves, and as you can see, we've connected this form and this form right here. So be aware that sometimes you can move multiple electrons when getting to one resonance form. In theory, all resonance forms should be drawable from any of the original resonance forms. You should always be able to move the electrons around any way you see fit, assuming you don't break the original rules. This brings us to our last type of resonance, which is benzylic resonance. Similar to allylic resonance, this is when you are adjacent or beside a benzene. So a benzene ring is a molecule that has 6 carbons, where there's a double bond every second carbon. Every single molecule here, or every single atom, more specifically, is sp2 hybridized and has 1 hydrogen. Now, why this is so awesome is that we are able to move those electrons, bond-to-bond arrows, to satisfy the positive charge, which moves the positive charge to this atom. And that's our first good resonance form. But now we can use the orange electrons and move them as well. And now we can use the blue electrons, right? We can move this positive charge all across the molecule. And so now, if we wanted to do the last step, we could use the red electrons and move them back to this double bond. And note that would take us all the way back to our original molecule. So being beside a benzene actually gives you 4 resonance forms. Once again, you'll notice that all the arrows I'm using here are bond-to-bond arrows, since we're dealing with a positively charged molecule. Now with the 4 resonance forms, we can once again draw a hybrid. And here, what's important to note is that the whole molecule is at some points double bonded, but the positive charge is going to be split over 4 different atoms. Now, this is assuming that all of these resonance forms are equally stable, and that is actually slightly incorrect, but for reasons that we're going to explore later in the course. For now, this is a good thing to understand, that benzylic resonance is actually more stabilizing than allylic resonance. Benzylic resonance is one of the best types of resonance you can have. With that in mind, we now have a good understanding of how positive charges can be stabilized via resonance. Let's take that understanding and move it towards negative charges.